iron 3 oxide reacting with carbon monoxide to produce iron and carbon dioxide. This is an oxidation-reduction reaction, or a redox reaction. This kind of reaction happens when one of the reactants gains electrons, thus reducing its oxidation state. In this case, the iron in the iron 3 oxide had a negative 3 charge. Then it gained 3 electrons to become neutral in the iron metal product. Now, if we have 7 kilograms of iron 3 oxide and 3 kilograms of carbon monoxide, how many kilograms of iron would be produced? Let's first look at how many moles of iron each of the reactants can produce if we had an unlimited supply of the other reactant. Since the molar mass of elements is calculated in grams per mole, we need to first convert kilograms into grams. In the conversion factor, kilograms are on the bottom since we want them to cancel out. Next, to change from mass to moles, we divide by iron 3 oxide's molar mass, which is 159.7 grams. Then, we use the molar ratio of iron and iron 3 oxide to get 87.7 moles of iron. Notice here that we had 3 significant figures in 7.00 kilograms at the beginning, so we should round our result to 3 significant figures. We'll use the same process with carbon monoxide. The quantity we have of carbon monoxide is also expressed in kilograms, so the first step would be to switch it to grams. Dividing by the molar mass, 28.0 grams per mole, gives us how many moles of carbon monoxide we have. Then, since there are 2 moles of iron for every 3 moles of carbon dioxide, we times the number by the molar ratio to get how many moles of iron 3 kilograms of carbon monoxide will produce, which is 71.4 moles of iron. As before, we round to 3 significant figures. By comparison, we can see that using what we have, we can only produce 71.4 moles of iron because we do not have enough carbon monoxide to produce 87.7 moles. This makes carbon monoxide the limiting reactant. And since we are trying to find the mass of iron that we can produce, we must times the moles of iron, in this case 71.4 moles of iron, with the molar mass, 55.85 grams per mole. Then convert it into kilograms to get 3.99 kilograms of iron, with the same number of sig figs as the beginning value. So, with 7.00 kilograms of iron 3 oxide and 3.00 kilograms of carbon monoxide, we can produce 3.99 kilograms of iron. Now, since carbon monoxide is the limiting reactant, we will use it after all the reactions. Then, how many kilograms of the excess reagent, iron 3 oxide, remains? Let's find out. If we are reacting 3 kilograms of carbon monoxide, we should be able to calculate the mass of iron 3 oxide it reacts with. First, convert kilograms to grams. Then, divide the mass by the molar mass to get the number of moles of carbon monoxide. For every 3 moles of carbon monoxide, there's 1 mole of iron 3 oxide reacting with it, which enables us to find how many moles of iron 3 oxide are reacted. Then, we can find the mass of iron 3 oxide reacted by timing it with the molar mass, then converting the result into kilograms with the correct number of sig figs, 3. This should give us 5.70 kilograms of iron 3 oxide. This is the amount of iron 3 oxide reacted with 3 kilograms of carbon monoxide. How many kilograms of it would be left then? The final step would be to subtract 5.70 kilograms from the initial value of 7 kilograms of iron 3 oxide, which will give us the final answer of 1.30 kilograms of iron 3 oxide remaining after the reaction. In this video, we went over iron ore in a blast furnace in an oxidation-reduction reaction aka redox reaction, the amount of iron produced with 7 kilograms of iron 3 oxide and 3 kilograms of carbon monoxide, and finally, how many kilograms of excess reactant will be left after the reaction. If you ever get your hands on some iron ore and happen to have a furnace that goes up to 2,800 degrees Fahrenheit, you'll know exactly how much iron you can make.